Section 5.4 in our book deals with exponential functions, and it shows how both to differentiate and how to integrate with exponential functions. We're going to split the section into two parts. In this part, we're going to look at how to differentiate exponential functions, which will be on the next test. And then after that test, or between that test and the final, I'll show you integrals that involve exponential functions. So first of all, let me define what the exponential function is. So in calculus, e to the x is defined to be the inverse of the natural logarithm. So in other words, it's defined by the property that natural log of e to the x is equal to x. So if we want to get a differentiation formula for the exponential function, we can just differentiate both sides of this equation. Now on the left, I need to use the chain rule, and the derivative of natural log of u, remember, is u prime over u. So the derivative of log of e to the x is going to be 1 over e to the x times the derivative of e to the x. And on the right side, the derivative with respect to x of x is 1. So now if I multiply both sides by e to the x, I get that the derivative of e to the x is e to the x. Now there's also a chain rule version of this. If I replace the x with a u, then the derivative with respect to x of e to the u is going to be e to the u times the derivative of the inside, which is u prime. So here's the chain rule version. So both of those will be worth memorizing. Let me recopy this formula off to the side. And then let's do some examples. Number 34 from page 348 asks us to find the derivative of e to the negative 8x. So using this rule, dy dx will be e to the negative 8x times the derivative of the inside. So e to the negative 8x times the derivative of negative 8x. And the derivative of negative 8x is negative 8. So I get negative 8 e to the negative 8x. Problem 35 is similar. Here we have y equals e to the square root of x, which we can rewrite as e to the x to the half power, like so. So the derivative of y with respect to x will be e to the x to the half times the derivative of x to the half. Notice I'm still following that same pattern. The derivative of e to the u is e to the u times the derivative of u. So this is e to the square root of x multiplied by the derivative of x to the half is 1/2 x to the negative 1/2. So if I simplify this a bit, the e to the square root of x is in the numerator. The 2 is in the denominator. And I can also move this square root to the denominator. So I get e to the square root of x over 2 times the square root of x. For a third example, let's look at problem number 42. In this one, y is equal to x squared times e to the negative x. So for this one, since the x squared is being multiplied by the exponential, I'll have to use the product rule. So y prime will be the derivative of the first times the second plus the first times the derivative of the second. Here, the derivative of x squared is 2x. And over here, the derivative of e to the negative x is e to the negative x times the derivative of the inside. And the derivative of negative x is negative 1. Simplifying a little bit, I can bring this negative 1 out in front. So this is a minus x squared e to the negative x. And then notice that I have an e to the negative x common to the two terms. And if I factor that out, I get 2x minus x squared. It would be possible to factor out an x as well, and there are situations where we might want to, but I will say that it's very common practice, if you have an exponential common to different terms like this, to factor it out so that you have a polynomial times an exponential. Let's also look at problem number 50, where y is equal to e to the 2x over e to the 2x plus 1. This time, we'll be using the quotient rule. So we'll have the denominator, e to the 2x plus 1, times the derivative of the numerator, minus the numerator times the derivative of the denominator, all over the denominator squared. So let's take those two derivatives in the numerator. I'll have e to the 2x plus 1 times the derivative of e to the 2x is e to the 2x times the derivative of the inside, which is 2, minus e to the 2x times, and then the derivative of e to the 2x plus 1 is going to be e to the 2x times the derivative of the inside, which is 2, plus 0. Let's bring along the denominator. And now let's see if we can simplify the numerator a little bit. I'm going to distribute this 2e to the 2x across this binomial. So that gives me 2e to the 4x plus 2e to the 2x. So I multiplied e to the 2x times 2 times first the e to the 2x and then by the 1, minus I have 2 e to the 2x plus 2x is 4x. And then finally, the 2e to the 4x and the negative 2e to the 4x cancel. And I end up with 2e to the 2x over e to the 2x plus 1 squared. And that's my derivative. For one last example, let's look at problem number 51. Here, y is equal to e to the x times sine x plus cosine x. So we'll need to use the product rule to differentiate this. The derivative will be the derivative of the first times the second plus the first times the derivative of the second. So let's take those two derivatives. The derivative of e to the x is e to the x. And I'll bring down the sine x plus cosine x, plus e to the x times the derivative of sine x plus cosine x. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Now let's distribute these e to the x's and combine like terms. Up here I have e to the x sine x plus e to the x cosine x. Down here I have e to the x cosine x minus e to the x sine x. So notice that the terms involving sine disappear, and these two terms are identical, so I can combine like terms to get 2e to the x cosine x.